session of the Research Seminars series hosted by Nomadic Labs. Today's speaker is Bas Spitters, an associate professor in the Department of Computer Science at Aarhus University. In this talk, Bas will give an overview of the ConCert framework for smart contract verification in CoQ. The ConCert framework has been used to model interacting smart contracts such as the DAO and a distributed exchange. It also supports Quickchick's property-based testing framework, which has been put to use to find real-world attacks. Finally, we'll also discover how to perform verified extraction from ConCert to the Camligo smart contract language. Feel free to ask your questions directly on the chat. A Q&A will happen at the end of the presentation.
Hello, thank you for the introduction. I'd like to tell you about ConCert. This is our smart contract certification framework, which we've built into the CoQ proof assistant. And it's unique in the way that we can verify, test, and extract smart contracts. This is work together with my postdoc, Daniel Anakov, Mikko Milo, who was a research assistant, and Jakob Nielsen, who was a PhD student. I work at the computer science department at Aarhus University, and we have a collaboration with the Concordium project. The collaboration is very much similar to what the collaboration that Tezos and Nomadic Labs have with the India Research Institute. And that's very exciting because there are two very serious projects that spend a lot of time on research and on science. And we have a very good collaboration, and I have probably 2 decades collaboration with India and the CoQ team. So I'm very impressed by the work that has been done by Tezos in this respect. So ConCert. So we use a proof assistant CoQ in for us to write smart contracts, and we do code extraction and property-based testing all in one system. So what is a proof assistant? Most of you will know, but let me recapitulate this very quickly. So a proof assistant is software for developing machine checkable proofs, or machine check proofs if you're done with your proof. And there are many applications in mathematics and computer science, and the proofs are developed in interaction with the users, but there's still a lot of automation built in. So we use tactics, decision procedures, SMT, or integration if you want. There's a lot of work, and this is by now standard. If you submit a paper to, for instance, the POPL conference, it will be very common that it comes with instead of a very tedious appendix saying that you've actually done your proof with your programming languages meta theory, you actually provide a formal proof. And you would prove things like correctness of compilers, type checking, and then another exciting feature is extraction of bug-free implementations. And I'll say much more about this in a minute. So we use the CoQ proof assistant, which of course has been developed by INRIA for 3.5 decades by now. It's a functional programming language with a powerful type system, and we can write both programs and their specifications in the same system. You could write a sorting function, quick sort or merge sort. You can define a predicate, decidable predicate in this case, saying that something is sorted. Then you can state a conjecture, saying that if you sort a list, then it will always be sorted, and then you can do 10,000 tests, and you can see here that in this case it's actually true. And then you can prove correctness. You can actually prove that the sorting function always returns a sorted list. Now what we're doing is actually modeling smart contracts in a proof system in CoQ. So contracts are, we model them as partial transition functions. So you take a call context, a message, and a state, and you return a list of, you return a new state and a list of new actions that are called. So you could call new contracts, for example. And we will write these smart contracts as CoQ functions. And then one of the important things that we're actually modeling inside ConCert is smart contract interaction. So one smart contract calling another one. And this is very important because this is one important source of bugs. And this is also very important in modeling these important smart contracts. And I'll say a bit about our testing framework. So CoQ, of course, is primarily based to do proofs, but it has a nice property-based testing framework. And we've used this successfully to find bugs in contracts. So here's the just a general overview of what the system looks like. So we have our smart contracts, then we have an execution layer. So this gives us the interaction between the smart contracts. Of course, we do proofs about these smart contracts, like functional correctness or some good properties about the interactions. We use the Quickchick. This is a pun on Quickcheck, which is famous from Haskell, to do property-based testing. Then we have these embedded in CoQ. Then we go to the MetaCoq framework. I'll explain all of this in more detail in a minute. I just want to give you a general overview of what this looks like. So we'll use verified erasure and optimization. Then we'll have an integration layer to actually connect it to real smart contract languages. And in our case, those are primarily Camligo and Rust. Of course, Camligo translates to the Michelson language that people may be more familiar with. What we've done is we basically looked around. So what kind of smart contracts are people actually interested in? What kind of things are, where do the bugs occur, and where's there's actually a lot of money involved. So we'll have, we have the escrow, which is a fairly simple one. Then we have boardroom voting, which allows people to vote in smaller groups, where you make sure that in the end you correctly recorded all the votes, but you know that the votes are completely private. So this is a very nice combination of smart contracts with a number of cryptographic constructions. Then we modeled tokens, the ERC20, then also the FA2 token that's used by Tezos, of course. We used the Brave browser, that's actually the browser I'm using right now, the basic attention token, and also the Concordium token standards. And then one of the sort of another big one that I forgot is the DAO, or the Congress, that I'll get to in a minute, and decentralized exchange, so decentralized finance. And that's another place where a lot of problems show up and where we can actually find them using testing. Here's a very simple example, which is a counter contract where you can send two kinds of messages. You can say increase the counter or decrease the counter, and then you send them, and these increase and decrease, they take an integer. So this is only there to show that we can work with side conditions. So if this is positive, then we actually update the state to increase with that number, and otherwise we decrease. And then we can show functional correctness of this contract. We show that if the message is an increase of a positive number, then we'll get that the next state is actually bigger than the previous state, and it's precisely increased by that much. And similarly for the decrease. We can also prove safety. So in the end, for any reachable state, the state is precisely the sum of all the increments and the decrements that were sent. So this is a fairly simple, of course, this is sort of the hello world. So it's the simplest contract one, sort of simplest contract one can imagine. But here there's already a bit of work involved to prove functional correctness and safety. So as I said, CoQ includes a Quickchick property-based testing framework, and we use this to test the blockchain execution traces for functional correctness, safety, and temporal properties. Like I just showed you, the functional correctness and safety properties. And in this way, we rediscovered known vulnerabilities or bugs in the DAO, in Dexter and Uniswap, iToken. We found something in the BET token, And there's no need. So of course now you can say, well, these vulnerabilities were not found by you, and it's always easy if someone points you to the vulnerabilities to find them again. But what we did was not so much use the information of the specific attack, but we just wrote down a straightforward specification of these contracts. And then by running these tests, you would actually find these vulnerabilities. We have a longer blog post about precisely the process of how to go about this. There's a bit of work involved. So the property-based testing, of course, is nice because it's completely automatic. There's still a bit of work involved to actually manually define generators satisfying the preconditions, because otherwise you would be generating general tests, and then often the precondition would not be satisfied and you would just discard them. So you would not find much information. So that there's a bit of creativity involved in getting Quickchick or getting the property-based testing to work. And now, because we have all of this in one framework, we can both show the presence of bugs, because Quickchick, if it actually, it will give you the counterexamples if the property doesn't hold, or we can use CoQ in the usual way to actually find prove the absence of bugs or absence of particular classes of bugs. So here's the setup we've used. So we use action generators, so generators for actions between contracts, and then an initial blockchain setup. And this gives us a generator for the blockchain trace, and these are standard combinators to put them together. Then we write testable properties, things like for all traces the following happens, or reachability, or some functional properties. Then we use the standard Quickchick framework, and then we output a result saying either passed or it gives a counterexample. So now this is very nice. But we're working with models inside CoQ, as you saw the counter contract. What we had there was just some contract written in CoQ, and of course it doesn't directly work on the blockchain. So how do we actually get it there? Now this is a common problem, and there's solutions, but we need to change this solution. So proof assistants have very expressive languages, and you can use the specification. You can use dependent types to write the specification in types. Then we can use code extraction to produce executable code in a conventional programming language. And this is available in CoQ, in Agda, in Isabelle Hall. And typically what you do is you extract to a functional programming language. So the standard CoQ extraction, it extracts to OCaml, Haskell, and Scheme. Well, of course, those don't directly run on the blockchain, and moreover, they're not verified. So that could still give us some problems in the that could introduce bugs. So that's something that we're addressing. So we've implemented the whole pipeline, the whole extraction pipeline in itself. Just to give you a spoiler, what we're going to do is to extract from CoQ, from ConCert, to Camligo, which is a language for Tezos running on, which is very similar to OCaml. So we implement the whole pipeline in CoQ itself, and then we use the meta programming through the MetaCog library. I'll say more about this in a minute. And we use the verified erasure from MetaCog that was already there. And this gives us a translation from CoQ to LambdaBox. LambdaBox was introduced in Pierre Luthezé's thesis. And this is an untyped functional language, which is sort of the core of Haskell, OCaml, and Scheme. And what this proves in MetaCog, this was already done. So this proves that the evaluation of the original and the erased terms actually agree. What we still need to do is add pre-processing with correctness guarantees, because if you just add pre-processing, then that's usually the problem, usually the place where you actually introduce the bugs, because you're trying to do all kinds of clever optimizations. We do verified optimisations to get more pneumatic and also a bit faster code. And we do translation of the data types to types in the intermediate representation. So the MetaCog project, which is now supported by Nomadic Labs, so this is a project in Nantes. So it consists of several sub-projects. So there's template Coq, which allows to do meta programming in Coq, and this reflects the whole Coq kernel into Coq itself, and then you have your quote and unquote functions as you're used to. There's the Quickchick, the predicative calculus of cumulative inductive construction. So this is the meta theory of Coq. And then there's a checker for this. So there's a type checker embedded into MetaCog. And then there's Erasure, and that's the Erasure that we use. So this Erasure gives us a translation from Quickchick to Lambda box, and it proves the computational soundness with respect to a weak global value semantics. Now, here you can see what this looks like, and as you can see, it's an entirely standard functional language together with a box construction that I'll explain in a minute. So what we need to add, or what we've added, is erasure of types and inductives because we're extracting to a type language, and optimisations. The regular erasure gives us far too much boxes, and that's something that we'd like to, or that we need to remove. So what we provide is an erasure procedure for types. So we go from the Coq types to ML types, or in this case, Camligo types. We remove their arguments, and we do that in a verified way. And we have pretty printers and integration with the runtime. So our smart contracts are actually running on the testnet. To Camligo, we also made a web application in this. We're using Elm, and we can also do it for Rust. So here's what this looks like in pictures. We have our ConCert, that's the picture that I showed you before. And then we go, by quoting, we go to template Coq, and there we do inlining, eta expansion of branches, and we actually generate some proofs. Then we go from there to Quickchick. Then we do erasure to Lambda box, but we actually, so the types are lost at this place, but we put the types back in. And then after we've done that, we do optimization pass here. And quite a bit of our work will actually be included in the general MetaCoq framework because it's useful more generally. Then these optimization passes can also be used in the CertiCoq project, which is a certified compiler for Coq, because it actually, CertiCoq uses much of the same compiler toolchain. But from here, from Lambda box, we actually print to Camligo and to other languages. All of this has been published in CPP, Certified Proofs and Programs, and we actually have a much longer paper available on the archive. All of this will be, I'll have references at the end of the presentation. I think, yeah, so the trusted code base, as you can see, it's Coq, it's the MetaCoq quoting that we have here, and then it's the printing and the integration with the target language. Camligo, for instance, has not been verified yet, but the printing that we do here is actually very simple. So you can inspect it by hand, and then you can see that it's very likely that there are no bugs there. Now let's look at so just to explain to you how this pipeline works. Let's look at an example. We have the usual fold right over lists, and then we can look at a safe version of the predecessor function on natural numbers. So this comes with a proof that the number is actually different from 0. So let's extract the following. So it takes a list of natural numbers, takes the predecessor, and returns the sum of those. Now, if we look at the standard erasure, then this is what we end up with, the fold right, and then the safe breadth and the safe sum. You can see there are all these boxes here where there's information that's not available in the target language. So if you would extract this to OCaml, then these boxes would need to be done by object magic. So here there are explicit type applications, and that approves here. Now what we do is we add the types here. So we first define what a list is, and again the boxes here and boxes here because we have the sigma type here, and then we have even more boxes. And now we remove the dead arguments. So as you can see, lots of boxes here, they're actually removed by this dead argument removal. Now all of this has been verified, and what we proved, that is, we proved Soundness with respect to the big step weak call by value evaluation relation that we have in MetaCog. So if in Coq this evaluates, the term t evaluates to the value v, then the same happens for the d-art t and v. We also have soundness of extraction. So if this reduces to some kind of erasable constructor, then the same thing will happen here after the extraction. So this is really the best you can hope for. So now we have fully verified extraction to lambda box, and to a typed version of lambda box, and from there we can print to a number of languages, including Camligo. So there are a number of challenges. So the question is, why is this not entirely straightforward? Well, a big thing is that we want to be very careful with the programs we put on the blockchain. So therefore, there's no object magic or no unsafe coerce allowed in Camligo, for example. There are no non-recursive data types, so we actually need to translate these by hand. There are no usually defined polymorphic types and functions. That's actually quite a big hindrance, but there's recently this has been merged into Camligo, so we're actually making progress on extracting more and more smart contracts. There's also only till recursion in Camligo. So there's some consequences. Some extracted code will not be well typed. Some till recursive functions are not supported, and we need to do remapping for certain collections, for arithmetic and so on, because we cannot define these recursive data types in Camligo. But Camligo provides a number of primitives, so we just need to do the remapping directly. And to do this, we provide a certifying pre-processing step, and we provide a translation table for remapping to the target primitives. This remapping, at least in an uncertified way, is a standard feature for Coq extraction. For instance, you would like to extract the natural numbers in Coq to introduce in OCaml to do a lot faster computation. So usually this is unverified, and here we actually have a bit more guarantees because we do some of this remapping in MetaCog, and we have a bit more control over this. So here's what the process looks like. We do a pre-processing state, then we do erasure, optimization, and then printing. So we can now add conversion preserving pre-processing steps. This is all done inside Coq, inside MetaCog. We can do new verified optimization steps to get much more idiomatic code or much more efficient code. We also provide a verified target language with respect to the weak call by value semantics. And then, so here's the whole process again. So we implement and verify it in Coq. Then we do the pre-processing, like inlining, specialization, and actually generating the proofs. Then we erase the proofs, and this is by our extended verified version of MetaCoq erasure. Then we do the optimization that I just explained. Then we do the printing. And then we can, if we want to extend this even further, we can add further pre-processing steps. We could also add further optimizations. And if you want, we could add new target languages. So if someone comes up with a new language for the Tezos blockchain, then it's quite easy to target this one also. So this is about the work that's already completely done. Now I want to give a few hints to work that we have in progress. Here's a collaboration with the Mi-Cho-Coq team. Mi-Cho-Coq is it's a verification framework in Coq for low-level Michelson code. And we have work in progress on actually integrating this with ConCert, because then we can use the ConCert testing framework, and we can also use the contract interaction that we have available in ConCert. We have a couple of models of contract interaction. We allow both depth-first search and breadth-first search. Meanwhile, since we developed this, Tezos has actually switched from one model to the other. But we still allow a number of possible optimizations there, and it's not too hard to define your own. So many things can be proved, irrespective of how the execution layer precisely works. Now, one thing I mentioned is that we can use Quickchick to find vulnerabilities in the old Dexter contract by writing down a very natural specification of Dexter of what you want an exchange to do. Basically, you want to have the constancy of the number of coins in circulation. And why could we do this? Because we could model contract interaction inside ConCert, so we could actually find these vulnerabilities. Now, after this vulnerability was found, so this vulnerability was not found initially by us, but we could recreate it. There's this new Dexter 2 project, which we've also implemented in ConCert. We found some minor discrepancies between the informal specification. So I should actually compliment the authors of both the contract, and so this was implemented in Camligo, but it was also had a very precise informal specification. What we have now is, during the implementation of Dexter 2 in ConCert, we found some minor discrepancies between the informal specification and the actual implementation, and the informal specification has been updated. So after fixing these, it's actually functionally correct. So the Dexter 2 contract implements the informal specification. We're working on proving safety, but we haven't completely finished that yet. Now, a final point that one would like to get to. So all smart contract languages, they have some kind of cryptography built in. Something that was recently added to the Michelson language, and that's used by a number of blockchain projects, including Concordium also, and a number of others, is the BLS pairing. So this is used for signatures, also in Michelson. And so these are pairing-friendly elliptic curves. So we're working on a verified implementation, and actually the initial benchmark for this is that it's only twice as slow as unverified Rust. So I'm very happy with the speed we actually obtained here. And this is because we're collaborating with Diego Araña, who's an expert on cryptographic engineering. What we've done is we put together a number of projects, and I'll show you this in a picture. We have a two-page abstract to CoqPL, where you can find much more information about this approach. So we start with HexSpec. HexSpec starts from the observation that if you look at the Internet Engineering Task Force, the Internet standards, then they usually come with a bit of pseudocode, and the pseudocode, of course, is nice, but it's imprecise. So we want to have a small domain-specific language to actually write down these internet standards and write down primitives. What they've provided is backends to both F* and to EasyCrypt, and then use this, for example, to connect a simple specification, which you can just transliterate from the pseudocode in the standard directly to Rust. And then from Rust, because this is a very small subpart of Rust that is basically monadic programming, pure monadic programming with state. So you translate this from Rust to EasyCrypt and to F*, and then you can check if you have an implementation of an algorithm in both these standard. The nice thing about hexspec is that this can be easily read, unlike the code in F* or in EasyCrypt or in CoQ. Hexspec is it's very simple Rust, and this can be read directly by cryptographers. So you can see that you actually have the correct specification of your cryptographic code. Now what we've done is we created a backend to hexspec in CoQ, because that's a system we like to use. So we have a functional specification here in CoQ, and we did this for the BLS curve, and we recently completed it for the BLS hashing to curve. So we have a functional specification here. Then we implemented the BLS curve using fiat cryptography. This is a library developed at a verified compiler written by the team at MIT, and this creates fast implementations of cryptographic primitives, especially finite field arithmetic. Now, what this is missing is loops and function calls, because it only generates a straight line code, and that straight line code, so that's resistance against timing attacks. So we could directly generate Rust by going here, but then there's a lot of glue code missing. So in fact, what we do is we go from fiat cryptography to Bedrock, and it has a small language here where we embed. This compiler has actually been verified. So we have our implementation here, and then we verify that the optimized code we have here actually satisfies the functional specification that we've derived here. So then we can see that our optimized specification actually compiles to something that's correct and fits the specification. And then from here we have an unverified printing to Rust, and we actually made it so that it's safe Rust. So we still have quite a lot of guarantees about memory safety and so on, just by the Rust type checker. So this is, so we have most of this working. What we're working on is actually making it even faster than what we currently have. And this should be manageable to speed it up even further. But even now, when it's only twice as slow, I think it is actually pretty fast, and it would probably be useful for quite a few applications where the verification, the correctness is more important than the speed. Now, here's another project that I've been involved in, and this is collaboration again with Nomadic, in this case with the team of Mi-Cho. So he has a project to work on F*, and this is one of the things that came out of this. And this is a close collaboration where we looked at tools like EasyCrypt and FCF and CryptHole. So there are ways in which cryptographers actually prove protocols to be secure by reducing them to hard assumptions like prime factorization. So what we did was to take a technology that comes from the Microsoft InReal lab, where they the Everest project, where they're trying to make a verified version of TLS. They have a proof technology called state separating proofs. So what we did was to put together general categorical framework for dealing with effects, this modular cryptographic proofs, and then foundational semantics that we actually made inside the Coq prover system. So this allows us to connect the high level of proofs coming from state separating proofs to semantics in Coq. So we have both the syntax and the semantics in Coq, and we verified the connection. We already verified quite a few protocols in there. One of them is Sigma protocols, which are a version of zero knowledge proofs. Similar things are also used in this boardroom voting smart contract that I mentioned. So one of the projects we currently have is to prove security, and this is mostly done to prove cryptographic security of the boardroom voting protocol. So we already proved correctness, functional correctness, but now we can also prove cryptographic security of this voting protocol by connecting it up with ConCert. So that's the last part that needs to be done. So just to give you a few conclusions so we can step back. We have a verification framework for smart contract interaction. We have extraction to Camligo, and this is actually running on the testnet. We have property-based testing for tokens, for the DAO, for decentralized exchange, and we have quite a bit of work on higher assurance cryptography that we're also integrating into this framework. We have code, papers, and presentations, blogs. Everything is available from our website here. Thank you for your attention, and I'd now like to take questions.
Thank you very much, Bas, for presenting this work. It's a very interesting line of work, and I'm a big fan of ConCert. I have a few questions for you. So the first one is about the Dexter2 verification. So you've in your presentation you've explained very well how you translate from Coq to Camligo, but here you needed to do the opposite. So you started from a Camligo contract that wasn't was originally written in Camligo, wasn't generated from Coq, and you needed to import it in ConCert to test or verify it. So how did you do?
The way I did this was to take a very clever student, and he actually did it. So he read the Camligo code and he translated it by hand. Actually, there's some more monadic notation in Coq, so the Coq code might actually be somewhat more readable than the Camligo code. It might be slightly more idiomatic. What we haven't tried yet is to extract it again, but it should look pretty similar to the original code. What would be very exciting to do would be to have better support for Coq over Camel, which of course is one of the projects that has been developed at or supported at Nomadic, and actually try to target that to Camligo and actually translate that to Coq directly. I think that would be a very interesting project. I'm not sure how much. I think it would be feasible, but I haven't tried it. But to answer your question briefly, is just the translation was done by hand.
Okay, so it's interesting that you talk about Coq over Camel, because indeed that's yet another complementary tool.
That would be the way to do it. Yes.
Yeah. So in the specific case of Dexter2, you could also use the specification that you wrote in Coq as part of the Mi-Cho-Coq verification of Dexter2. So you could do that for any contract that has verified implementation in Mi-Cho-Coq, but of course that there are many contracts out there that aren't yet verified. Okay, thank you for this. So here again, it's probably a place where Mi-Cho-Coq can also
that would be interesting to have, and that's, I mean, one of the things that excites me from having a closer connection between Mi-Cho-Coq and ConCert to actually bridge that gap and try to avoid redoing these things.
Yes, that would be very time saving. Okay, totally different question. At the beginning of your presentation of Coq, so at the very, very beginning of your talk, you mentioned SAT and SMT solver integration. Is it something that you use?
No, this was a general statement that's possible. Of course, there's the work on SMT-Coq that we've been following, and we've been looking at the snipe tactic that is integrated there, and we would like to use it, but we've been going back and forth, playing with it. Doesn't seem to be entirely ready yet.
Yeah, that's my impression too. But the friends at SMT-Coq are very eager for feedback. So if you've
yes, no, so that's something that will certainly have another go at in the near future. I have so we did a couple of projects in EasyCrypt, and there it's actually quite surprising how well it works. And one of the things that we're doing also with SS Proof, which in some way is a re-implementation of part of EasyCrypt. We would like to get a similar convenience for in SS Proof as one has in EasyCrypt. So that's also one of the things that we'll be looking at to see whether SMT-Coq or maybe just first order in Coq could actually help there. But so the nice thing about SS Proof is that there we're very close to something that's well understood in EasyCrypt. We can just re-implement those protocols in SS Proof and then do the proofs in a more modular way, and then see at the level see where SMTs is used in EasyCrypt and see how long that looks. Well, I mean, how long the corresponding code is in SS Proof. So far, it certainly seems feasible to do that. And so one thing that has been done by my PhD student Nikolai Sidorenko, he took some implementation of Sigma protocols, which is a class of zero knowledge proofs. He did that formalization in EasyCrypt and then redid it in SS Proof, and that actually went quite smoothly. So to do that translation. So it seems that at least in that case, the supporting Coq was pretty good.
I'm sure they'll so the friends at SMT-Coq will be happy to hear. We have a question from Guillaume Claret, the author of Coq of OCaml. So he's asking if you plan other backends to extract to smart contracts.
So there is extraction to the Rust smart contract language, or the Rust language, which is used for smart contracts. We don't have anything on our list, any other things on our list at the moment. One thing we did was, I mean, it's another thing we did was to do Elm, and Daniel Annenkov, he actually wrote a nice web application that then with a small layer actually had application written in Elm that was completely extracted from Coq in a verified way. So that's a good demo from the Elm set that can actually be used. Anything that's sufficiently close to the lambda calculus would work to extract to, but it's Obviously, what a lot of projects are doing is looking at solidity, but it seems to be too far from functional languages or pure, at least pure languages. One thing I should say is there's a language that is developed by eToro, that they use for derivatives, and we have an interpreter for this. So this is a domain-specific language for derivatives. We have an interpreter for this in ConCert, and that actually extracts well to Camligo. And we actually did some statistics and some measurements, and the gas, the energy or the gas it uses, it's very limited. So it actually works well to just have the interpreter running on chain, and then you can use this to write as a domain-specific language. That can also be done for similar domain-specific languages. There are a number of projects that have such domain-specific languages specifically for finance, and that should work in much the same way. So we've done that. So we've written the interpreter, and that works well. So but that's one layer extra. So you first extract to, say, Camligo, and then you have the interpreter running there.
Mm-hmm.
Guillaume, does that answer the question?
I don't know, but he has another question.
Oh, yes. So the next question is, does it make sense to write it directly in CoQ,
yeah.
or first write it in Camligo? I think that's a general discussion of whether you want to how do you want to develop correct programs, and that can be done in two ways. You either use extraction, or you use something like Coq over Camel or Haskell to Coq, and you could even compare this to something like liquid Haskell, which adds refinement types to Haskell. There's at least one paper which compares these two approaches and shows that Haskell to Coq seems more efficient than liquid Haskell, for example, in the few examples that they tried. So the nice thing about what one could do is to try to write correct Camligo programs by having a close integration with something like Coq. I see no problem in integrating that directly into ConCert. Actually, we did a bit of work in that direction, but then well, not for Coq over Camel, but to have the AST of a functional language in Coq, and then actually import it into ConCert. Another project that, of course, has a very much the similar flavor is the program machinery. The work by Mi-Cho-Coq that he did in his thesis was to provide the Russell language, where you would have an embedded. Well, he was thinking about OCaml. So you write a piece of OCaml code with pre and post conditions, and then you embed it into Coq. So that could also be, and especially connected to MetaCog, that could also be a very valid way of doing this. So I think that that's a very good question by Guillaume, and I don't think we know the answer yet for regular programming languages. So if you want to write correct OCaml, what is the best way of doing that, or correct Haskell? And the same problem comes back here for smart contract languages, and I think we should try all these approaches.
Thank you for the answer. I think Guillaume will be interested in the reference to the paper you mentioned that compares both approaches. So if you can find it, we could add it to the description, maybe. Okay, we have another question from Owen Miller. He's asking if there are any bounties for the project you do. if you would contribute time or code and get paid for it.
Bounties for finding bugs, or?
Yes, or verifying code, I guess.
So we do basic research, and we don't have a bounty project for that. There's probably a possibility to apply for I mean, there's a possibility to apply for small grants both at Tezos and at Concordium, I think. But I'm not giving out these bounties.
So we formulate the question as can someone hire you to verify a DAO?
Okay, so I think that's so. My understanding is that Owen would like to contribute and would like to find funding for it. Yeah, so you can ping me online, and then I can give you the things I know about, and you should find the information about the Tezos grant program, and they'll have more information. Does that answer the question, Owen? I think so.
So let's switch to another question of mine. So do you have feedback to give to the LEGO team? So do you, because in your presentation you sometimes face limitations of LEGO. So you mentioned, for example, the lack of arbitrary recursive functions and inductive structures. So I guess part of them could be maybe implemented in LEGO. Maybe some of them would require a change to Mikkelsen too. Do you have comments on that?
So the biggest obstacle for us was the lack of polymorphism, because that makes it hard to extract. So this was partially addressed, and we're looking at I think it has polymorphic functions now, but not polymorphic data structures yet. So there's, if I'm not mistaken, but we've been working with the Camligo developers to actually improve this and improve the extraction. I think that this polymorphism was one of the hurdles that avoided us from extracting. That was actually the biggest one. And we're looking forward to continue to collaborate with them to make sure that we can extract all the programs we're writing in CoQ, because I mean basically we're writing the functional programs, and we would like to extract them to Camligo. But so to phrase it quickly, so generally the collaboration with the Camligo team has been pleasant, and they've been adding the things that we needed, and I mean they also need it for their own sake.
Yeah, well said. Thank you. I have a more technical question about Lambda box. So I was a bit surprised to see that you use a non-type intermediate language, even though your source and target language are typed. So if I understood correctly, you reinject type information in the middle of the pipeline. So why? So usually the intermediate language is the language you control the most. So it's a bit surprising that you're facing. Yeah, you needed to do that instead of replacing it with a typed version of Lambda box or something like that.
So the reason for that is that that's the way extraction works. So extraction in CoQ, it takes dependently typed program, makes it into an untyped program, and then the type inference in either OCaml or Haskell actually refines the types. And then sometimes you need to annotate it with object magic, for example. We cannot do this because there's no object magic, and because the type inference of Camligo might not be as strong as the one for OCaml. And so if we would start entirely from scratch, I think we would have kept the types. But what we did was to work on this big body of work in MetaCog, where the types are already erased. So we just did an extra pass to put the types back.
Okay, so that's
that was mostly an issue of reusing the work that had already been done, which was substantial.
Yes, that's very understandable. We have another question from Nicolas Yash. So Nicolas is asking, how far away are we from a good automation in proving smart contracts with ConCert? So what do you think about automating verification proofs?
So we have a notion of contract induction, which really, I mean, is sort of a specific induction principle, and that has reasonable automation for handling lots of trivial cases. We're in the process of refining that a bit and making it more modular, but there's still quite a bit of work to be done by hand, and I think also that's something that we should expect, because I mean, in general, proving properties about programs is hard, and I don't think there's a reason why we could expect to have this completely automated. But we have we have a bunch of tactics, and we have some specific induction principles that help quite a bit to do these proofs.
So do you have numbers in mind regarding, for example, the number of lines for verifying a contract versus the size of the source code of the contract itself, or something like that?
No, I don't have them by hand, but it's reasonable. It's as you would expect from proving things about other programs.
Thank you very much. I think we are reaching the end time for the session. So I'd like to thank you again for sharing your knowledge with us, and thanks to the audience too for attending this research seminar session. So thank you everyone, and goodbye.
Thank you very much.